Hey, let's make a start. Definitional work to start with. Again, I'm recording this. The PDF will be available at all leading retailers, well, at least on Google Classroom. So if you fall behind, don't stress about it too much. Okay, so we're going to start with the definition of an ordered pair. So an ordered pair, when you see that phrase, it just means X comma Y. So always X followed by a Y, okay? Always in that order. 3, 2 cannot mean the same as 2, 3. It's always in that order. A relation. Now, this is the reason why I've started with something simple like that is because a relation, we can use the phraseology of an ordered pair to describe it. A relation is a set of ordered pairs which may have a rule. That rule, and I saw there was a little bit of confusion last lesson actually. That rule is what we would tend to call no, you know what? Don't add the word function. I'll explain why later. Tend to have that may have a rule. So honestly, for a relation to be a relation, and you should have come across this language before. I'm just recapping really. For a relation to be a relation, you don't need a rule. If you could just list a whole set of ordered pairs where the first one always corresponds to an X coordinate and the second one corresponds to a Y coordinate, I can graph it. It might look weird, but I can graph it. It's a relation. Okay, so that's all it is. Often we will write a rule down because when we write a rule down, we can use that rule to describe a whole heap of pairs all at once. But ultimately, what you're doing with a relation is you are either writing down all the pairs that make the relation, or you're writing down a rule which describes all the pairs. Okay, now I'm trying to talk to you like someone, like a group of people who have already heard the word relation before, have already seen it in action. So it's part review, but I'm also elevating my language there to talk about ordered pairs and that kind of stuff to try and connect your brain to how we're talking about stuff. But if it doesn't make sense, you need to ask questions. So a relation is just a set of ordered pairs. If the set of ordered pairs is dense enough, we can draw a line on a graph for it. But that line is just a graphical picture of that set of ordered pairs. Okay, I won't overtalk it, but ask questions now. This is conceptual, so you need to ask conceptual questions, not how do I, but what does this mean, blah, 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 blah. Last chance before I move on. Okay, this is why I'm a little bit behind, I think, because I wait too much. A function is something we are familiar with. A function, no worries, is a relation. It's a special relation, effectively. It's a relation such that each x value has only one corresponding y value. Okay? So if we think of a function or the picture of a function, last year you would have been exposed to the idea of a vertical line test. So if we draw a picture of a relation, I won't do it on the video / on AirSketch here. I'll just do it on the whiteboard if I've got a texter. So I'm just drawing a picture of a function like so. The picture has the Cartesian axis, so an x-axis and a y-axis. If I take any value on the x-axis, this is the x-coordinate, right? On the ordered pair, it's the first number. If I take that coordinate and go up to the line, that makes a single point on that line, just a single point. And if I then go across from that line to the y-axis, I'll get the second coordinate, or the second coordinate of the ordered pair, the second number in the ordered pair. That's what makes a function a function. Okay, the fact that it has that property. So the graph is a picture representative of these ordered pairs. So if the x coordinate was 3 and the y coordinate was 2, this is the ordered pair 3, 2. Very, very specific. Okay? I don't hit that function again when I go up or down vertically. However, there are in a relation, if it does have more than one output, more than one y value for an x value, it's a relation potentially, but it's not a function. I'm going to look at a non-example now. So the non-example I've got up there is x squared minus y squared is equal to 1. That is a rule. It's a nice simple rule. It's an equation. I can choose the x coordinates to put in there, and then I can solve for y, right, which we're going to do verbally. I can solve for y. Therefore, I can get a table of values. If I can get a table of values, I can map those tables of values, and then I'm able to graph it effectively. So the non-example is x squared plus y squared equals 1. I'm going to deliberately choose minus 1 and 1 to start with, and then I'll fill in the rest. So if I use x equals minus 1, I would replace x squared with minus 1 squared. Minus 1 squared is 1. So we have 1 plus y squared equals 1. Subtract 1 from both sides, I'd get y squared equal to 0. And so therefore y is equal to 0. Is that okay with everybody? If I don't have to write it out, it's so much better. Similarly, if I have x equal to 1, then 1 squared is equal to 1. 1 plus y squared equals 1. So y squared equals 0. And so y would equal 0. So when x equals 1, y also equals 0. That's fine. I've got the same y value twice here, but because they correspond to different x coordinates, that's fine. Okay? It's fine that it corresponds to the same y coordinate because they've come from different x coordinates. There's no dramas there. That's still, if it's got that relationship, it's still okay. A really simple example of a function that works like that is y equals 2. Doesn't matter what you put in as the x coordinate, the output will be 2. So it'll be 1, 2, 3, 2, 4, 2, etc. So that's okay. That's a function. You know what that is. It's a horizontal straight line, right? That's fine. Now, let's have a look at x equal to 0. If x equals 0, what happens to this term here? Disappears effectively, right? 0 squared is 0. So we're left with y squared equals 1. And if y squared equals 1, what does y equal? Positive or negative 1 pip. Yep. So it's not just 1, it's plus or minus 1. When we square root 1, we do get 1. But because y is a variable, we then need to say, well, y could have started off negative because when we square a negative, it's also positive. So it's plus or minus 1. So this bit here is where we have an issue. Okay? This bit here, what we're basically saying is that with with 0 as an input, the output could be either 1 or minus 1. And so therefore it is not a function. It's a relation, we can graph it, but it is not a function. Similarly, we can go when x equals 2, we would have 2 squared is, oh, that's a bad choice, Richard. Oh, might just change that. I don't know if I can be bothered. Okay, I'll change it because it's just doesn't. You can probably figure out for yourself why that doesn't work. It's not in order now, but I don't care. I'm going to live on the wild side today. Okay, so when x equals a half, when we square a half, we get a quarter. Yeah? Half times a half is a quarter, so there's a quarter there. Subtract it from 1, and I'll get 3/4 over here. And if I take the square root of 3/4, again, a square root symbol is involved, and so it's plus or minus that. So it's plus or minus √3/4. I'm going to write the answer slightly differently. I'll let you figure out why it's like this. It's plus or minus √3 all over 2. I'll let you figure out later why it's all over 2. But again, plus or minus. And so we definitely get a sensible result, but we don't get a result that we can do much with. Just PS, I've got something over here which has got nothing to do with this. Don't worry about this at the moment. If I do that rule, if I go x squared plus, do you know what this will give me? I'm going to draw something. Yeah. Little teeny tiny circle. Okay, so it gives you that and that. So it's a little teeny tiny circle, and 1 is the square root of 1 is the radius of that circle. So if I go 25, it gives me a radius 5 circle, for example. And you can work it out for yourself why it does that. But there you go. So that's a relationship, or a relation, I should say, but it's not a function. And what we talk about is it failing the vertical line test. So it doesn't matter what value I choose here between here and here. I'll choose x equals -2, but it could be anything that you use. There's a vertical line test fail there because if I go from the x coordinate, I get 2 different y coordinates. Okay, so that's why we talk about it failing the vertical line test, because effectively from the x coordinate, I can reach the y coordinate of the rule in 2 different locations, hence not a function. What do you think? Any questions? Any clarifications needed? Roger Dodger? Okay, back we go. Domain. This should be stuff that you're familiar with already. Someone want to give me their definition of a domain? Sunny? Yep, great. All possible x values for a function or for a relation. Yep. Anything like that would be fine to write down. I'll just formalize it slightly. Instead of saying all possible, which is legit, absolutely 100%, I'm going to say the set of. Oops, don't want to do it in green though. So I'm deliberately using the word relation here, remembering that all functions are relations, even though not all relations are functions. So functions are a subset of relations. All functions belong to the idea of relations. So it's the set of x values of a relation. I tend to use the idea of the inputs of a function or a relation. But as you can see, x squared plus y squared equals 1. It's a bit loosey-goosey, isn't it, talking about what's the input there, other than the fact that it's the letter x, and we sort of translate that to input, but it's a set of inputs. The range is the y's. I think we should, if you know the domain, you should be able to figure out the range. So that's the idea of a set. Okay, and I'll put this in. Didn't leave room for it, but just to remind my students from last year, and in case it's useful for those I haven't taught before, I tend to use this rather weird kind of aid to memory. Dixroy. Domain is input, it's X values. Dix. Range is output, it's Y values, Roy. So if you can kind of remember Dixroy, you'll probably be able to remember which one's which kind of thing. If you remember Rickstoy, then you're stuffed. So make sure you get it around the right way. Okay, this is kind of a little bit new, perhaps, on the slide 4. This notation here, this is a function f defined as that dot dot or such that it takes a set of input values, domain, and maps them or makes an image to the set of numbers in a range. So f, how I kind of say it is f goes from D to R is how I say it. F goes from D to R. So all the values in D map to a value in R. So you just need to think of D and R as sets of numbers. Sometimes those sets are what we call dense sets, which means you can't list them, and other sets you can. So the next notation is this one here. It's again a bit more formal than what we've done in previous years. This here, this little symbol here, I'll even zoom up so you can sort of see it a bit more. This little symbol here is like a little tiny E, right? It's drawn like this, whoop, and then a bar in the middle. I want to say it's a lowercase epsilon. I'm not 100% on my Greek letters, but I think that's what it is. So that means is an element of. An element of is a fancy phrase to describe it belongs to or a member of. So what this says is that X belongs to, is a member of, is an element of. X is an element of the domain set. And I'll give you an example now, just ones that you're kind of familiar with already. If I wrote X belongs to square bracket 1 comma infinity round bracket, that means all the possible real numbers between and including 1 all the way up to infinity. So every single number above and including 1 is how you would read that. X belongs to the set of numbers made up of from 1 to infinity and beyond, if you like. Any questions on that? I'm sort of going a bit slowly because language is kind of really important, and if you sort of glaze over the language, then you just never get into the right habit. Okay, the second one is very similar. Y is a member of R, the range, or Y is an element of R, and that R might look different. So it might look like this. It looks like a coordinate, but it's not. This part of it really reinforces that we're definitely not talking about a coordinate -1, 1. Y belongs to the set of numbers, or real numbers, between -1 and 1, not inclusive of -1 and 1. So remember, round bracket is not included, square bracket is included. We always use round brackets for infinity and negative infinity because infinity is an aspiration, it's not a number. It means that it's going that way, it's always going that way, but it's not a specific number. That's how we write it. So we don't want to see notation which is like y is greater than 3 to describe the range. We want to use this kind of notation. This is called interval notation. There is set notation as well. I'll need to get back to you. I can't remember whether you officially need to know how to do set notation or not, but we do need to formalize what we're doing a bit more. Now, the last bit I'll zoom up on as well is this notation here. There are some sets of numbers that are so common and so specific in what they mean that we tend to write them with special symbols. I'll start with the one that people will be maybe less familiar with. Who knows what that means? It doesn't mean I've got a Zorro complex. It's both of these relate to a set of specific numbers. Now, I don't want to get too far down the rabbit hole, but it comes from I can't remember what the German is, but they both come from German for what they represent. And what happened, right, is when mathematicians they do a lot of writing. When we've got special sets, what we would do if we were on a computer is we would make the letter bold. So that's just a bold R. But if I was writing it, it kind of looks like that. It's a bit tedious to write it in bold. And so what they did is they sort of said, well, let's make it like with an extra line on the like that to make it like pretendy bold. Okay, so it's an R with an extra bar on it, but it's R, and the R stands for the set of real numbers. Z, which is a bold Z, but we just put an extra bar on it like that when we're writing it, is the set of integers. Okay? There are other sets like that as well. There's a rational set, irrational set, and complex set. Yeah, I think that's it, but there might be more. Yep. Yeah. I just never know which way's off, though. We'll try that. Feel free to open the windows, Charlie, as well, if you like. That will help. The noisy kids are gone out. Okay, so just a reminder, please, would someone please remind the class what an integer is? Yeah, that'll do. Whole number, positive, negative, or zero. Okay, whole number. And real number? Sorry? Yeah, but that's sort of using the word to define the word, which is never a great definition. Hamish? Yep, includes decimals, terminating decimals, non-terminating decimals. Any number is a bit tricky because there are numbers that are not real, but they're still numbers, complex numbers they're called, imaginary numbers. So but yeah, as a loose definition, any number you can think of that you would normally use is a real number. So the square root of 2 is a real number. 3 is a real number. Pi is a real number. All of those are real numbers, okay? They're real numbers. The square root of -7 is not a real number. It's a complex number. It's an imaginary number. Okay, so therefore all integers are real numbers, right? All integers are real numbers. We call it a subset. Integers are a subset of the real numbers, but just so that when you see them, you know what they're talking about. All right, so if you want to, you can annotate what I've written here. So real numbers, and that is integers. So if I wrote X as a member of R, I'd be saying X is a real number. X belongs to the set of real numbers. If I said X is an element of Z, I'd be saying X is only an integer. All right, need to move on to some slightly more, some more languagey stuff. Any questions? Okay, spinning on. Restricted domain. Um, Okay, when a relation has a reduced set of numbers as its domain, it still might be infinite, but if it's been reduced, we say that that is a restricted domain. You are already familiar with this. Do you remember the application problems that you've done in previous years? And you had to come up with a function, and then they would say, graph the bit that makes sense for the application problem. And so maybe it was this, and you had to go, oh, well, it can't be this, and it can't be that, and it can't be 0 either, so I'll put a circle there. And that was the actual function. Sorry for the video, I'm just modifying the drawing on the board that I did. And I've erased the bit that's before y, before x equals 0. Does that kind of ring a bell, that you've sort of drawn a graph where there's a bit that doesn't make sense, so you don't draw it in? So that's an example of a restricted domain, right? So for an application problem, you might be saying, well, x has to be greater than 0. And so it's a restricted domain. Otherwise, if you don't describe what the domain is, it's implied, it's expected that you're talking about all real possible numbers for the domain. So we call that, I think it's called an implicit domain, I think. It says it in your textbook somewhere, so you can fact check me later, but I'm pretty sure it's an implicit domain. What I wanted to show you was a couple of specifics. You can annotate them for yourself, or maybe they'll just make sense when you look at them. This is an example of a restricted domain. You can probably figure out what it means. So you just put a little plus there. That one, you can probably figure out what that means. Hamish? Yep. And that one is, Hamish, you do that one as well. Yep. Chan? Beg your pardon? No. Excellent question. Neither of them include 0. 0 is neither positive nor negative. It doesn't include either of them, which is why I think there's another way of writing it as well. Sorry. I tend to write it like this. Do you remember from probability union means join these two things together kind of thing? So this means all positive real numbers plus that little squiggly bracket there. Just, I haven't drawn it very well there. I'll draw it nice and big so you can see it. It's those braces. That's what I've drawn, but very poorly. So that squiggly bracket notation is actually set notation. So this says the set of real positive numbers joined with the set that includes the value 0. Okay, so I've added two sets together to make a new set. This would be 0 onwards. There is other notation available. Okay, and I don't want to bog you down too much by over talking the notation, but there is other notation that allows you to do basically the same sort of thing, but with squiggly brackets and stuff. Obviously, interval notation could be used as well. So this would be the equivalent of 0 to infinity. Same notation. Okay, but yeah, interval notation isn't always the way to go. Okay, you know what? I'm basically going to leave it there so you can have some practice, and then I'm going to return in about 20 minutes' time and discuss something else. We're going to look at transformations. But before I put down some textbook work for you to do, does anyone have any questions about that language? Okay, so in your practice time for the next 15, 20 minutes, all I want you to do really is I want you to practice identifying domain and range and writing down what that is using some sort of notation to see how you go. I don't have the page number again, I apologize, but it is exercise 1B, question 1 and question 10, don't do anything else, and 1C, questions 3, 4 and 5. And yeah, I'll give you 15 minutes, so till 12:20 to see how far you can get on that. Good luck, everyone.